So we're in the chapter on energy and the first law of thermodynamics. We've covered a lot of material, and it's basically I need to cover a few more topics, but we have a closed system, and we have the first law and energy balance for that closed system. And it can be for a process, it can be for a cycle, and then it can be per unit time. It can be a rate-based equation. And then we're going to have to cover some generic power, refrigeration, and heat pump cycles, and introduce coefficients of performance as well as efficiencies. First clicker question. So I'll give you a little more time, 45 seconds. Fill in the blank. This is just like it could be on the exam. It says blank conducted experiments in the year blank with a paddle wheel to measure the mechanical equivalence of heat. Who did it and what year? A, B, C, D, or E? Get your answers in. All right, we're all in. So let's take a look at the results. Pretty good. So Joule did it, and he did it with the paddle wheel in 1845. This Benjamin Thompson, he did the cannon boring earlier, 1798. He's also renamed, or they was given the honorary name Count Rumford in the Holy Roman Empire, but his born name was Benjamin Thompson. And then this is just the wrong year, right person, wrong year. And Watt did a lot of things, but James Watt didn't do it. It's Joule. Joule. True? Very good. So before really that time period where they were seeing the equivalence of energy in different forms, they had the caloric theory. And they said if you heat something up because of a temperature difference, you could have a transfer of something called heat. And it would take something else, if you brought it into a system, it could change the internal energy of the system. Or really what they did was they said, here's the mass of the system, the specific heat of the system. It would change the temperature. It would be realized by a temperature change. It would heat it up. So things would cool down. As they cooled down, they transferred heat out of them. And other things, if they were cold, they could be warmed up by bringing heat in. And so energy in the form of this caloric theory was conserved and measured, etc. Then they had the mechanical equivalence. So they said, look at mechanical work. If you push on something and you make it move, it can lead to a change in the kinetic energy and or a change in the potential energy. These were two distinct. What did the first law of thermodynamics do? It brought them together. And so you brought them together, and because the application was a heat engine where you're trying to burn something, bring in some heat into that engine to turn something, produce some work out, the sign convention that work out is positive and heat in is the positive direction. So when you combine them in the first law, we would have the first law says Q in minus work equal to, so the only thing is dealing with that sign in front of these two, lead to a change in the internal energy, lead to a change in the kinetic energy, and or lead to a change in the potential energy. And those are the three forms of energy that we, not energy transfer, but energy storage in a system that we study in engineering thermodynamics, not 4, 5, 6, etc. We just really emphasize internal, kinetic, and potential energy. Okay, for this class, that's our three forms of energy storage. A gas in a piston cylinder assembly undergoes a constant pressure process at 300 kilopascal from an initial volume of 0.6 meter cubed to a final volume of 0.66 meter cubed while being heated. So the way we have a constant pressure process in a piston cylinder apparatus is just put the piston so that it can rise. And when it rises in a gravitational field, the weight doesn't change, the atmospheric pressure above it doesn't change. Free body diagram on the piston basically gives you that the pressure below doesn't change, even though it rose in the piston cylinder apparatus. So the heat transfer comes in, and if you wanted to, you could kind of sketch it. That's as a cheesy sketch here. The piston's risen, and so this is state 1, this is state 2. And so maybe we talk about, well, the pressure at 1 started at 300 kilopascal. What did the pressure at 2 at? Well, it ended at 300 kilopascal because it's a constant pressure process. The volume at 1 was 0.6 meter cubed, but it expanded a little bit. The volume at 2 is 0.66 meter cubed. Exactly what is that volume? That's the volume of the trapped gas that's in that piston cylinder apparatus. That's the volume of that trapped amount of gas. So the piston raises, you have more volume, there you go. The change in the internal energy of the gas is 63 kilojoules. Try to organize that piece of information. That's saying, well, you know some internal energy to start with, you know some final internal energy, but you know what? That final internal energy is greater than the initial internal energy by 63 kilojoules. That's one way of writing it. Or you could just rewrite that equation and say U2 minus U1 is equal to 63 kilojoules. It went up. Does it matter if it's a plus or minus in front of that 63? Yes, it does. Avoid plus minus sign errors. Okay. The atmospheric pressure above here is 1 atm, 100 kilopascal. That's pressure atmosphere, all right. Considering the gas as the system, often you have to be clear. I'm focusing on this system. What exactly is this system? The gas. Is it the gas and the piston? No. Is it the gas, the piston, and the cylinder? No. Just the gas. All right. Evaluate the work and the heat transfer. We'll stick with the sign convention. Okay. Do you think that Q will be positive, 0, or negative? Clicker question. A, B, or C? Let's just see how you go. Q, do you think it's going to be positive? Answer A. Do you think it's equal to 0? Answer B. Do you think it's negative? Answer C. Or maybe I should say D. I have no idea. You could put D if you like. It's the wrong answer. D is not the right answer. But if you want to put D, you can. We got to be done sometime, right? Sorry. Well, why did most of you say it's positive? It's right there in the problem statement, right? It's talking about it's being heated. Where is that said? It's being heated. Heated. Heat is coming in. Being heated. How are you going to get a gas to expand at constant? Heat it up. Heat it up. All right, so that intuitively it makes sense, plus the wording in the problem. All right, so how about the work? Can I tell anything about the work? I'm asked to calculate the work as well as the heat transfer. The work, let's think about this. Do you think it's going to be positive, equal to 0? Can't spell 0, try that again. 0 or negative? Answer A, B, or C. The work. The work transfer. Is it going to be positive, 0, or negative? A, B, or C? We're done. Why is it positive? The system is the gas, and it's pushing back the surroundings. It's pushing back the surroundings. It's doing work on the surroundings. I know it's not a shaft, but it's boundary work. All right, very good. So it's positive. So also, let's see. Here's another clicker question. The answer, it doesn't tell me what units to give the answer in. So I will give you a choice. Answer A, I think it's going to be newtons. Answer B, I think it's going to be kilojoules. Okay, kilonewtons, put a kilo in front of it. I answer C, I think it's going to be kilowatts. Or answer D, I think it's going to be Newton times meter divided by second. What are the units of the answers that I'm looking for? What are the typical SI units for the heat transfer or the work transfer? Kilonewtons, kilojoules, kilowatts, or Newton meter per second? Do you need more time or are you good? Everybody in? Good? Well, let's see where you stand. Woohoo! Pretty good, right? That's not bad. It's this. It's joules or kilojoules. True? All right. Let's continue on. So we know the symbols. We want the W in kilojoules. We want the Q in kilojoules. It's for the process. Sometimes we'll put 1, 2, 1, 2. Sometimes we don't put the subscripts 1, 2. But there's only one process to talk about. Leave off the subscript going from initial state 1 to final state 2. How could I calculate this work? How could I calculate that work? You could calculate it from first principles by kind of definition. Work is associated with pushing something, and so we have boundary work on a gas, integral P dV. First principles from mechanics. Or a lot of times we can get work deducing it from the first law. It's a participant in the first law. It's in the first law. Heat transfer, same thing. First principles, conduction, convection. It's rare that we do it at this level. Did I mention you have a whole class in heat transfer waiting you at the 4,000 level? Yeah. You'll do more there, okay? But for Thermo 1, we basically don't do much in first principles. We don't do the conduction, Fourier's law, convection, Newton's law of cooling, or the radiation with Stefan-Boltzmann law. What we do is deduce Q using the first law, energy balance. So in this case, integral P dV. That's not too hard to do because the pressure is constant, and so it's just an integral V, so it's V2 minus V1. So we stick in that we find that the work is equal to 300 kilopascal times the change in the volume. 0.66 is the final, 0.6 is the initial. Both of them have units, meter cubed. You do the unit conversion, and you find that the work is 18 kilojoules. Box the answer. Maybe even put, if you had, it's part A, put A there to emphasize it's part A, or part B. Here we don't have part B and C and D, so, but there you go. You're going to get full credit? You're going to get full credit. All right. Now, if we use the first law, we say Qin minus the workout equal to the change in the internal energy. Well, the change in the internal energy is U2 minus U1, is it not? Guess what? That was given to be 63 kilojoules. We're asked to calculate the work. I'm sorry, we just calculated the work, 18 kilojoules, and we can calculate the Q. Q is going to be 81 kilojoules. True or false? True. There you go. Now, let's build up on this problem. Ready to go to the next? Yes, sir. The atmospheric pressure does not matter, does it? Because you're given that the pressure here is absolute pressure, and it's always 300 kilopascal. Let's say somebody upped the pressure of the atmosphere to 200 kilopascal. Can you still make this problem work by changing maybe the weight of the piston? Would you increase the weight of the piston to keep the gas at 300 kilopascal if the atmospheric pressure increased? If the atmospheric pressure went up, increased, then you would need to reduce the weight of the piston in order to maintain 300 kilopascal. Do a free body diagram on that piston. Right? And we're about ready to do that. Next slide, because we have part B for this problem. Ready to go to part B? Part B says, same problem. The piston is well insulated from the gas. That's one piece of information. Everything, sometimes I give you superfluous information. Sometimes I say, and the moon rose last night at 11 p.m. It's superfluous. It doesn't need to be solved. But often in engineering, we don't give superfluous information. It really throws students for a loop. It's like, why did you put in there that the moon rose last night? Well, that's just the way actually the engineering world works. And you have to deduce as an engineer what's essential and then what's not essential. So anyway, that's a piece of information. The piston is well insulated, and the piston moves without friction in the cylinder. Consider now the piston as the system. What was our previous system? The gas. Now it's the piston. Is it the piston and the gas, or the piston only? You got to be careful because it does make a difference. It's the piston only. All right. Calculate the work and the heat transfer and the change in potential energy. So I'm asked to solve for Q, the work, and the change in the potential energy. Now, all right, one of these is really easy. Which of these is really easy? It's even easier than the work. Work is easy, but which one's really, really, really easy? Q. Why is Q really easy? Let's see. If it's well insulated, how much heat was transferred into the piston? So this I do every now and then. I will, did you read the problem? Do you understand what well insulated means? It's like, hey, it's a freebie. Okay, but sometimes students drop the freebies. Now, somebody says, are you going to take off because I didn't put kilojoules? Zero is zero. Somebody says, I want you to travel a distance of 0. It doesn't matter if it's 0 millimeters, 0 miles, or 0 kilometers, or 0 feet, whatever. Travel a distance of length 0. What units? Doesn't matter. True? I have no money in the bank. I have no $10 bills, no $100 bills, no $1,000. There's no $1,000 bills, but you know what I mean. You got no money. It doesn't matter what, I don't have a nickel. So that's one of the things where here you can leave a unit off. Just try this. What's the difference between 0 joules and 0 kilojoules? Nothing. All right. So that's optional on the units right there. Now, how about the change in the work? Now, there's two works that this piston is doing by moving. First of all, think about the pressure is acting down. That's atmospheric pressure. Is it pushing against something as the piston moves up? Yeah, the atmospheric pressure. It's doing work on the surrounding known as the atmosphere above it. What is that part of the work? That part of the work would be to the atmosphere, and that's going to be a positive work, and that's going to be the integral PDV, which is basically the pressure of the atmosphere times how much it pushes it back. That's the same volume change that we had before. The same volume change, which was, let's put in our numbers, the atmospheric pressure, 100 kilopascal times 0.06 meter cubed. And so we find that the work that pushes back the atmosphere is, what is that, 6 kilojoules, right? 6 kilojoules. Now, there's also pressure right here. That's our gas pressure, and it's always constant at 300 kilopascal. So there's, maybe you think about this as the work of the gas below. But if my system is the piston, is the surrounding doing work on the piston? Or is the piston doing work on the surroundings? Which way is it? The gas is doing work on the piston. So from the perspective of the piston, it's a negative work transfer. It's absolutely a negative work transfer. So this is a negative. The 300 kilopascal times the same volume change. Well, this is all turned to kilojoules. So that becomes negative 18 hold it, 0.06 times 3, 18 kilojoules, right? So what is the combination work that the piston is doing against these two pressures as it's rising? It'll be a work of the piston, the net is a negative 12 kilojoules, meaning okay, let me do this now. Let's go to part C, because I think you answer part C here. What is the change in the potential energy of what? Our system. What exactly is our system? The piston. All right, well, how do I calculate the change in the potential energy of my piston? There's two ways. Go to the first law. Write the first law for the piston as it undergoes a process of basically going up, being lifted, okay? So if you do that, you'll say Q into the piston minus the work done by the piston on the surrounding. You have a surrounding on top, surrounding on bottom. We just calculated that. That's a negative 12 kilojoules. Is equal to the change in the internal energy, the change in the kinetic energy, and the change in the potential energy. Is that true? Is that a good first law? Okay. Why is Q 0? Well insulated. Why is change in the kinetic energy 0? There's no information about its speed. And I need its speed squared, and then I get its mass. And there's no information about that. How about why is the change in internal energy 0? There's no friction to turn mechanical energy into heat. There's no heat transfer because it's well insulated. Everything says there's no temperature change of the piston, no internal energy change of the piston. Guess what? The change in the potential energy is, can you tell, negative W. W is negative 12. Did I do that right? Yeah. Somebody says there's another way to calculate the same answer. Let's do it the other way. Let's go back to mechanics. Because somebody says, I'm going to try and squeeze it in right here. The change in the potential energy will be the mass times G times the change in the height. How many people were saying, that's what I need to do? That's more intuitive to me. That's how I got through physics and statics and dynamics using equations like this. Now in thermo, I got to think about this equation, first law of thermodynamics. But my mind was saying, give me the weight of the piston, mg, and then give me the change in elevation of the height, and I've got it made, right? So let's do this a little bit. Let's go and do the free body diagram, FBD, of that piston. What is coming down? The weight, which is mg. What's acting up? It's hard to show it, but it's the pressure times the area, pressure of the gas. What's acting down? The pressure of the atmosphere times the area. I don't know the area. Leave it in the equation. It'll cancel out in a minute. So from a free body diagram, mg, which is the weight, is equal to the pressure of the gas acting up 300 kilopascal, minus the pressure of the atmosphere acting down, that's why it's a minus, it's 100 kilopascal, times the unknown cross-sectional area. True or false? Okay. We just worked on this part of that equation. Now let's work on the delta Z part of that equation. Okay. They said there was a volume change. The area of the piston didn't change, just the height of the piston changed to accommodate that volume change. So what's the relationship between the volume change? Let me tuck it in right here. I break my own rule, but you see I'm fighting for space. On your paper, on your exam, try to kind of work in columns, okay? But what it is the final volume is equal to the area, the cross-sectional area of that piston times the final height, and the initial volume is the area times the initial height. So the volume change is going to be that area times the height change. True or false? And then what was the weight, mg? Well, it's the pg minus pa times the area. I just messed up here. This delta Z is the volume final minus the volume initial divided by the area. Now the areas cancel. There you go. So I didn't even need to go to the first law. It's probably better because we're studying thermodynamics to go to the first law. But I could say, oh, the difference in pressure between the top and the bottom, 200 kilopascal. What's the change in the volume? 0.06 meter cubed. Do the math. 12 kilojoules, the change of potential energy. So it seems like a different approach, same answer. Okay? When you have two answers, don't box them both. Just box the one you got the best confidence in. How's that? Yes?
Could you just use the word, like the change in kinetic energy plus change in potential?
There was no change in kinetic here. And you're right, both of these parts dropped out. So this is purely a conservation of mechanical energy form. It's only mechanical energy form. You're absolutely right. Yep. Okay. Thank you very much. Let's move on. Now we want to talk about is putting cycles on the PV diagrams. I know this can be tricky and convoluted and difficult for some students at the beginning, but let's just work through this a little bit. Let's say I have a diagram. Typically the pressure is the y-axis, the volume is the x-axis. That's our PV diagram. Maybe put it meter cubed, put it liters, whatever you like. Maybe put over here kilopascal, maybe put bar, maybe megapascal, whatever you like, okay, for the units of pressure and the units of volume. And what we do is we often put processes on. So let's start with this one just for example. I'm going to start right here at state 1, and I'm going to go to state 2 as an example. There's on my process. You should be able to interpret that process a little bit, right? Tell me one thing about that process. There's many things you could tell me, but what is it? One thing about it. It's constant volume. And is it pressure going up or down? Pressure's going up. Maybe we follow it with another process over to state 3. So what are the dots? States. What is the line in between? Process. And it's really important what direction you're going. Oh, I'm going from 2 to 3. All right. Sometimes you put a little arrow like that to indicate the direction of the process. Tell me a little bit about process 2 to 3. Constant pressure. Compression. Compression. It's being compressed. Right? All right. And then let's finish it out. You could have 3 or 4 or 5 processes to make a cycle. The simplest one really is 2 processes to make a cycle, but that's kind of boring. So often we stick with 3. Here's a return. There. From 3 back to 1. Now I tried to put a little curvature to that line so it's not a straight line. But you could put a straight line if you like. But here I put a little curvature to that line. Tell me something about that process. It's expanding. It's expanding. That's a big conclusion, right? And the pressure is coming down. Where is zero pressure? There. All of them have atmospheric absolute pressure above zero. There's no absolute pressure below zero, right? Okay, so where is zero volume? Here. All right. So let's talk about the works for each of these. Let's talk about the work 1 to 2. What do you think? Work 1 to 2. The classic question is it positive? Is it zero? Is it negative? Which is it? Is it positive, zero, or negative? Work 1 to 2. Let's ask a clicker question. Get your points up. So this is A, B, or C. The work for the process 1 to 2. Oh, it's positive. I can tell. Or it's equal to zero. I can tell. Or it's negative. I can tell. You got 5 seconds. Do you need more time? Oh, didn't make it. Sorry. Sorry, I tried, but I didn't get there. All right, so let's see where the class is at. All right, so we go back to our physics, and the physics instructor, either in high school or was in university physics, they put their hand against the wall. And they said, I'm now going to push on this wall. I'm going to exert a force on this wall. Here goes. Force is going up. I'm really pushing that. Force is going up. I'm pushing on this wall a lot. The force is really high. True? All right. Now, how much work did I do on the wall? I'm pushing on the wall with a great force. How much work did I do on the wall? You remember that demo? You didn't go get your money back from your physics teacher. Come on now, that's so easy. But you got this right, didn't you? You did get it right, so you learned something somewhere. So anyway, there's no movement, no dx. I don't care what f is. The integral f dx, if there's no dx, is zero. No work. Same with gas, right? I have to have a non-zero pressure. That's always easy to do, but I have to have a change in the volume. Here, do I have a change in the volume going from 1 to 2? So the integral P dB, when dB is 0, is 0. The area under a straight curve going up and down is 0. All right, so the work 1 to 2 is 0. How about the work 2 to 3? Can you conclude what it is? Let's do it out loud. 2 to 3. It's negative. It's negative. Work 2 to 3 is less than 0. It's negative. How about the work 3 to 1? Positive. Work 3 to 1 is greater than 0. Okay? Now, we talk about, let me do this. Work of the cycle. What's that mean? You just add up the work for the first process of the cycle, the second process of the cycle, and the third work of all of those processes to complete the cycle. This one is equal to 0. This one's positive. This one's negative. Oops, I got them backwards. This one's negative. This one's positive. The work 2 to 3 is visually the area under that curve. The work 3 to 1 is visually the area under that curve. The red was negative. The blue was positive. What's the work of the cycle? Visually, it's the area enclosed on the PV diagram by the cycle. So the net work of the cycle is the area enclosed. And because it's going this direction, I get all confused. Is that clockwise or counterclockwise? Counterclockwise. It's counterclockwise. That means it's being compressed at high pressures and expanding at low pressures. So the work net of the cycle is either positive, negative. Help me. Can you see which it is? It's negative. It's negative. The net work of the cycle, this is larger magnitude than that in this case. What happens if I have a different cycle? Let me scoot down and quickly sketch it. Here's PV diagram. PV, I'm going to compress, I'm going to expand, I'm going to go like this. That's kind of almost the same cycle. I'm just going in a different direction, right? Here I'm expanding at high pressure. Big positive workout. I'm compressing at lower pressures than what I expanded at, so it's negative but a smaller negative. Hence, this is a net positive work of the cycle, and it's equal to that area. It went this way. It went clockwise on a PV diagram. True? All right. So one of the things we really, really like PV diagrams because we can interpret the work. Now, you have to work a little bit more for the Q's, but for each one of these, you could have a Q1 to 2, a Q2 to 3, and a Q3 to 1 back again. But you have to be given more information about it. Oh, the temperature didn't change, or the internal energy didn't change, or it's adiabatic or something. No heat transfer. Okay? But the work you could do visually with the PV diagram. I got a few minutes here. I'll try my best. The gas undergoes a cycle in a piston cylinder assembly consisting of 3 processes. 1 to 2 is constant pressure at 1 bar, going from this volume to another volume, and they give you a positive work. If it's a positive work, which way is it going on a PV diagram? Is it going right to left? Is that it? Positive work? It's expansion. That's right. That's right. It's going that direction. And then it's followed by a PV compression with the constant internal energy. What's that look like? It's going to look like that. It's got a belly up, kind of concave upward shape to it. It's not a straight line. So we think, oh, we'll start at state 1 and go to state 2, and then this will be a compression along a PV is equal to a constant curve. And then we have a constant volume process. On a PV diagram, what does the constant volume process look like? Straight up and down. So we stop at 3 so that we come straight down and we hit 1. That's our cycle. I did that fast. I did that much faster than you can do. You have to go slow when you do homework and get ready for the exam. So we sketch the cycle, calculate the net work of the cycle. Well, to calculate the net work of the cycle, I would say give me the work 1 to 2, I'll add it to 2 to 3, and I'll add it to 3 to 1, and there you go. That's how I calculate the net work of the cycle. One of these is 0. Which one is 0? 3 to 1 is 0 by inspection. Okay. What about the work 1 to 2? Integral PdV, and I love that constant pressure. So it's just P1 times V2 minus V1. But you know what? They gave it to us in the problem statement. They gave us 1.5 kilojoule. How about work 2 to 3? Somewhere along the line, I'm going to have to do some work. I'll have to do some calculations. Can we do the integral PdV? Sure, that's the work 2 to 3 from V2 to V3. That P is given by the equation that it's equal to the constant divided by volume dV. What is that constant? Well, I can evaluate it at P2 V2. That's the constant. And I integrate from V2 to V3. Did I encourage you to look at the first worked out example problem in this chapter? Did I say, hey, that's important? That's what you're doing right now. You're just redoing the first worked out example problem in this chapter. And what you get is you get that P2 V2 times the natural log of V3 divided by V2. Guess what? Analytic expression with a little calculus gives you the work from 2 to 3. In the interest of time, I'm just going to tell you that you plug in the numbers on that. I've got to find my notes, sorry. Is this right here? Nope. I don't know where my notes are on this. Is this? Yeah, 1 bar, 0.025, 1.5. Yep. All right. You have to find V2, all right? And actually, you use the equation for the work 1 to 2 to find V2 is equal to V1 plus, it's the work 1 to 2 divided by the pressure at 1. And so you calculate that the final volume after at state 2 is 0.04 meter cubed. You put that in for this V2, you know V1 and V3 are the same, and you calculate that work 2 to 3 is negative 1.88 kilojoules. Hence, the work of the cycle is equal to negative 0.38 kilojoules. That's the answer to part B. Answer to part C now. Calculate the heat transfer for the process 1 to 2. Well, usually don't do it from first principles. This is first principles for the work transfer. Often we deduce Q from a first law. First law says that Q 1 to 2 minus the work 1 to 2 is equal to U2 minus U1. Did I write it correctly? Neglecting changes in kinetic and potential energy. Okay. And so the Q 1 to 2, what I'm looking to calculate, is equal to the work 1 to 2 plus U2 minus U1. Now I look all over this problem statement for some other information that I can use. Look at this information right there. How would I use that information? I would say that this is U3. True? See how I made that change? So it's U3 minus U1. Then I look at the problem statement and I say, oh, what did they just give us right there? So what we see is that this is equal to work 1 to 2 minus U1 minus U3. So it's equal to the positive 1.5 kilojoules minus a negative 133.5 kilojoules. And the Q 1 to 2 comes in at a whopping 135 kilojoules. Answer to part C. On a problem statement, if I say sketch the diagram, this is one of those problems where you don't have to box it. All right? You don't have to box it. I know that boxing an illustration is not helpful. All right?